Welcome everybody on Zoom. Welcome everybody in the lecture hall to this new week of Information System for Engineers. We'll finish what we started last week about the ecosystem around SQL. And then we'll move over to how to make queries faster, which is the whole benefit of using a declarative and functional language. So I have two questions for you first. Here's the first question. I told you about this three-tier architecture that many people refer to. And you basically need to find the one that is not part of this three-tier architecture. Is it the web server, the business logic, the database server, or the browser? Three are part of it, one is not. It doesn't mean it's not part of the ecosystem, right? But it's not considered one of the three tiers. We have a majority, but it's not a clear majority between the business logic and the browser. Oh, something's happening. Is there a flip? Yes, no. Ah, there is a flip. Well, I have bad news. It's the browser that actually is not considered part of it. Of course, people might have different views, right? But typically, when you refer to the three-tier architecture, what you mean is there is the database server, which is accessed with SQL. Then there is the business logic, which is typically using, some Java, C++, whatever code there is that is going to build the SQL that is shipped to the database server. And then there is the web server, which is in charge of shipping over the HTTP, the HTML pages, the pictures, and so on, right? And all that together constitutes the server. The browser is kind of a fourth layer, which is on the client side. That's what's on your laptop. And then you might have seen on professional networks, these people calling themselves full stack developer. These are the people who basically touch all of this. Okay. Then there is another question for you. I told you that even though some people might directly use SQL, for example, if you're sitting in front of your Jupyter notebook and you have a project like a master's thesis or a semester project and you want to query your data, then you're directly going to type SQL in the notebook. However, there are many environments in which it's more automated and SQL is actually generated dynamically on the fly via computer programs. And this is what we call a host language. So a host language is typically an imperative language as opposed to a declarative language. And this is basically the business logic, right? So the question here is, how is SQL typically interfaced with host languages? In other words, how is SQL created in the business logic layer? Multiple answers possible. So the first is with a library providing functions that take SQL queries as string parameters, or inlining SQL queries into a host programming language such as C with a preprocessor translating them to library calls, or is it using SQL as the host language itself and inlining Java, Python, or C++ imperative code inside a do imperatively statements, or is it with libraries providing iterators with which one can imperatively iterate over the rows and columns of a relation outputs by a SQL query? Okay, let's see what you said. All right. And the majority turns out to be actually correct in the sense that all these answers are correct answers. The only thing that doesn't exist and I completely made up is these do imperatively statements that you inline Java, Python, or C++ in SQL. That doesn't really exist. There are extensions of SQL that extend it with imperative features. One of them is PL SQL. And there is, I'm not going to name it, but there's a banking software company in Zurich that actually uses a lot of this PL SQL. And the others are true as well, right? So there are libraries where you just put SQL in a string and then call a function with that SQL query in a string. With caution, I told you about SQL injection attacks, that you have to be careful with where the string comes from. Particularly if you directly copy paste from what you got from the visitors of the website. Then you can inline SQL queries into a host programming language, and then you directly have SQL syntactically within the language. This is what probably looked very complex to you, because indeed it is very complex and not easy to read, right? But this exists. And finally, there are libraries that provide iterators, and then you can iterate over the rows. That exists as well, right? Typically, you see a lot of these libraries that iterate to generate HTML dynamically. Like, for example, if you go to some online shop and you look for products, then typically it's going to do, I'm oversimplifying, right? But when you search for a TV, let's say, it's going to do a select from where will filter from your search. And then you have limit 10 to paginate, right? And offset 0. And then the offset, when you click next on the next page, then it adds 10 to the offset every time, right? So you paginate. So basically, this is a SQL query that is created. And what you get from the SQL server, the database layer, is rows in a table, right? That contain these 10 results that you want to display. But you need to turn that into HTML because it has to be rendered in the browser, right? And typically you have codes that is going to iterate over the row, and it's going to generate dynamically the rendering and all the fancy look that you get in your page, right? For whom is that clear? All right. Okay, so now getting back to the slides, and we continue. Okay. So basically, all these things with the host language and the way you interface SQL in a different language, it's mostly going to be computer scientists that are going to do that, right? This is really pushing probably to the limits for people who are not computer scientists. So this is why you shouldn't worry too much if you're not fully comfortable with that, right? This is really what software engineers are doing every day. For you, again, for projects later, probably the most common use case will be a Jupyter notebook. You type SQL queries and you query your data in that way. Or maybe, who knows, that you want to build a PHP website with SQL. This is also something that is quite easy to learn, actually, to do. And then you can have a website that dynamically generate pages from with a SQL backend behind. Okay. So again, these are the 3 layers and the client on top. That's kind of a fourth, right? So the database servers with SQL, the application servers with the business logic, the web servers that ship over the HTML and all the contents, and the clients, meaning the browser. Okay, and here again, that's what I said some of you might actually deal with, because this is something that even non-computer scientists like to teach themselves, is to learn PHP and to dynamically generate HTML. So this HTML, these are the angle brackets that you see, right? Table, TR, TD, so this is all HTML tags. And yeah, it's quite, at least it was back then. I don't know if it's still very popular today, probably still a bit, but yeah. Okay. And this is another popular way of doing that, probably closer to Pandas or, you know, SQL Alchemy, which is another way than SQL to do things. So you can either write SQL, as you see on top, right, generate a SQL query, but there are people who prefer to use function calls within the imperative language, so who prefer to do it as is below, right, by calling count, group by, outer join, and so on as functions. Personally, I prefer SQL. I think it's much easier to actually write in SQL. It was meant to be intuitive, but it's a matter of taste, you could also argue. Who just, as curiosity, who prefers SQL? Okay. And who feels more comfortable with the bottom version? with the function calls? Less of you, right? Okay. Okay, so this is a bit as expected, right? So hopefully I managed to convince you that SQL is quite convenient to use. All right, so now I have the second part of this lecture on the SQL ecosystem that I would like to now finish today. What is this about? Well, until now, when we looked at SQL, it was mostly just you. You have the database PostgreSQL on your laptop, maybe in Docker, and then you write queries, but you're the only one writing these queries. There's nobody else, right? So if you update the database, you will see your own updates, but that's pretty much it, right? But now imagine that you have a website with PHP and SQL, or you are a big online shop with millions of people connecting every day to your database. So your database will get plenty of queries and plenty of updates, millions a day, right? And this is actually not trivial at all when you have to deal with many people accessing the same database. And now I would like to make you feel why it actually creates some problems. But the good news is, since we have PostgreSQL, PostgreSQL basically takes care of it for you. This is one of the benefits. The other benefits of having an actual relational database management system is that this all comes for free. The management of all these issues. If you do not use a database management system, then of course you have to deal with this yourself, and that can become very tricky. So this is one of the really nice features that PostgreSQL and other systems have. They can handle transactions and concurrency control. So I have two people here connecting to the database, and I have here bank balances of random people. And Alice here on the left is writing a SQL query, and she wrote SQL select balance from statement where name equals Albert. So by now, you know that this is a selection and a projection, right? So you select name is Albert and you project to balance. So the result is going to be all at the same time. Come on, you know. 1,000, yeah, exactly, yeah. Okay, and then Bob is issuing the same query, right? He's also working on his laptop, connecting to the database, and he's gonna get 1,000, thank you. Exactly the same. So now, oh wow, I think I clicked, maybe it's Bluetooth that is acting up now. Okay, so now Alice is sending an update to the database, and she's using SQL for that. So she's updating the table statement, setting the balance to 2,000, where the name is Albert, right? So now that's going to change the database. That's an update. So now it's updating this to 2,000. And Bob, right after that, is doing the same. They don't know about each other, right? They're just both connected to the database. And now Bob is setting the balance to 3,000, where the name is equal to Albert, right? So that changes the balance here. Now, this is Alice executing this query. She doesn't know about Bob. That's another user. My question is, what does Alice expect to see? 2,000, right? She expects to see 2,000 because that was her update. But now she's surprised. She sees 3,000. That's the sort of things that happen when several people use the database, right? And now Bob, of course, is going to see 3,000 as well, right? Okay. So now this is the perfect example of how not to run a bank if you don't want to lose billions of dollars and have a lot of unhappy customers. That's probably a very bad idea to run a bank like that, because you probably want more features and safety in place so that that sort of thing doesn't happen, right? In particular, if you go to an ATM and you want to withdraw money, as you can imagine, there's a lot of things in place to make sure that your account is going to be debited if and only if you actually get the banknotes in your hand, right? So this is why we have a lot of features that's commonly called transactions, right? We can do transactions, and transactions are basically here in order to avoid that kind of surprises, right? So the goal of transactions is basically to make it feel that you're the only one using the database, and you don't have this sort of weird behavior because of other people using it at the same time. So transactions are here to provide some level of isolation from each other in order to feel like you're the only one using the database. Of course, it's not forever, right? When you have a transaction, it's maybe for 1 or 2 seconds until you're done, right, with what you've been doing, and then you come back and might see some other updates, right? But within the transactions, it feels like you're the only one. So if we had a transaction mechanism like that, this couldn't have happened, and maybe Alice would have still seen 2000, and maybe Bob would not have been allowed to actually make that change until Alice is done, right? Okay. So now I wanted to show you a bit of theory. There's a lot of theory on that, right? It can be hours and hours of courses in computer science. But I wanted to show you one aspect of that, one algorithm to make you feel the sort of things that are actually done here with transactions. If you look at what is making things go wrong here, it's a lot about these updates here that are depending on each other, right? In particular, let's look for dependencies here, right? What happens before what? So for example, we have what we call a read-write conflict between this read here, you read 1,000, and this write that writes 3,000. Why am I saying that it is a conflict? I'm saying it's a conflict because if you swap the order in which these two things happen, it's going to change the results. Because if you first look at the balance and then you see 1,000 and then write to 3,000, the result here is 1,000. Imagine that it was the other way around, that you first had this executed with set to 3,000 and then you read, then you would have had 3,000, right? It would change the result here. It depends if it's before or after. So this is why I put this little arrow here that basically enforces the order, that says the order is important. We read here before we write there. This is called a read-write conflict, okay? Now we have another one here. We also have here, because time flies like this, right, top to bottom. So we have here a read by Bob that precedes a write by Alice. Here too, the order is important because if Alice had done her update before Bob's reads here, Bob would have seen 2,000. So I put this little arrow here as well. That's a read-write conflict. Then there's write-write conflicts, which is about the order in which two updates are happening. Where is a write-write conflict here? Zoom? Yes, exactly, the two pink boxes, exactly. This is a write-write conflict. Why is that a conflict? Because here too the order matters. If Alice first writes 2,000 and then Bob writes 3,000, this is called last write wins, right? Whoever is last to write has the final result. So since Bob was the last one to write his update, 3,000 is what is going to remain in the database, and 2,000 got overwritten. If we swapped the two and Bob would write first and then Alice, then we would have instead 2,000 in the database. So we have a write-write conflict. Can you guess the third kind of conflict? Write-read, right? The other way around. So here we have a write-read. For example, if Bob wrote 3,000 and then Alice reads 3,000, then this is called a write-read conflict. And here we also have write-read when Alice writes 2,000 before Bob writes. Bob reads, right? But of course, there's the other one in the middle, right? But we still put an arrow in there. Whenever we see a write to the same place as there is another read, we put an arrow. That's it. That's the algorithm. Okay, and now we just abstract away, like remove everything around that. So what do we get? This is a graph. This is known as a graph. There's a whole theory in mathematics called graph theory, where basically a graph is made of nodes and edges, right? So here we have 6 nodes, and we have 1, 2, 3, 4, 5 edges that connect the nodes together, right? We have 2 kinds of nodes, the pink and the green ones, right? So the pink ones are the writes and the red ones are the reads. And when we have an arrow from a green to a pink one, that's called a read-write conflict. Then we have an arrow to pink, that's called write-write conflict. And pink to green, that's called write-read conflict, okay? So we have all of these conflicts. Now, here's a more abstract way that we would write things down. Let me explain what that means. A lot of exercises actually are often given like that in textbooks. This here is a list of reads and writes. R means read, and W means write, okay? What is the order here? Well, it's basically top down, right? This, from top to bottom, right? So Alice reads, Bob reads, Alice writes, Bob writes, Alice reads, Bob reads. Now, the subscript here is the person, the user. So this is Alice, Bob, Alice, Bob, Alice, Bob. And what's in the parenthesis is what is being accessed, read or written. So here A is for Albert Einstein. It's just whatever, balance there is. Now I realize bank secrecy, but anyway, Albert Einstein here, right? Six times the same. It's just because here I only consider the single place that everybody reads and writes, right? But in general, there could be several places that you access. For whom is the notation clear? RW subscript for the user and in the parentheses what is accessed. Okay. But then that's great because now we can look at other things in a more abstract way, right? So now let me give you a different order of reads and writes. So again, R and W is the same, read and write. Now I didn't write Alice and Bob, I wrote A, B, and C. So you can imagine it's Alice, Bob, and Charlie. And we have A, B, C here in the subscript. And alpha and beta, I just used Greek letters. Alpha and beta just means that there's 2 places in the database that are being read, right? So there's a place called alpha and a place called beta. So what happens here is that Alice reads alpha, Bob writes a new value to alpha, Bob reads beta, Charlie writes a new value to alpha, Alice reads beta, Charles writes a new value for beta, Alice reads alpha, Charlie writes a new value for alpha, and Bob writes a new value to beta. This is what happens. Now, here's the interesting things we can do with that. First, we can try to build a graph in exactly the same way as before, right? How do I do that? Well, remember that when we did that, this list of actions, read and write, it's written like text horizontally, but it came from some top-down structure, right? Where here it's left to right, and here it's top to bottom, knowing that we had everything there was Alice and everything there was Bob. So how can we do the same here? Well, probably we're going to have Alice here, then Bob here, and then Charlie here, right? And then all of these here will come top to bottom. So this is what you get, right? So who would be able to do that? That's quite natural, right? I'm just spreading all over 1 per row, and I just put it in the column depending on the subscripts, right? So you see here, all the subscripts are A, all the subscripts are B, all the subscripts are C, and if I go every row in order, I get exactly the same order in there. Now, I need to put back my arrows for read-write, write-write, and write-read conflicts, right? So let's do it together. Can anybody give me conflicts there? Yes, maybe the catch box, or the microphone. We have a hand microphone today, here on the left. So let's try to figure out all of the conflicts.
The first line. Bob writes and value to alpha without
this, right?
Yeah.
Exactly. This is a read-write conflict. Yeah, very good. So indeed, that is true. We will put an arrow here. Anybody else? Yes?
This alpha gets rewritten a bit further down in C.
Yes, from here to here, right?
Yeah.
Yeah, that's called a write-write conflict. Can anybody maybe give me a write-read conflict? Maybe on Zoom. Anybody on Zoom sees a write-read conflict? Oh yeah, then let's go to you. Yeah, indeed. I see on Zoom too. Let's read what is on Zoom and then we'll look at you. So, oh yeah, it's let me reopen the window. So you said, Charlie writes to beta, and then we have second one. So you need, what an important point, that's actually a very good point, moment to make the point. If you have a conflict, it needs to be alpha alpha or beta beta, right? If you have alpha and then beta, this is not in conflict because you're looking at two different places, right? So it's really good that we got this example. So indeed, there is no conflict. If it's alpha and beta, then there is no conflict between the two and we don't put any arrow, right? So thank you for the suggestion. Let's go to you again now for what you wanted to suggest. Do you still want to contribute a conflict? No more? Yeah, okay. So let's see if we find one. That would be, so it needs to be alpha beta, and it needs to be write, then read. Does anybody see a place where there is a write and then a read, but both must be on alpha or both must be on beta? Yes, I see on Zoom.
Yeah, so we have one WC alpha and RA beta.
C alpha and this one here? I think that's the one, right? So that's the proposition you have. Correct? WC alpha and RA alpha.
We got another one.
Yeah.
First entry of C and a third of A.
First entry of C, this one, yes, absolutely. This is correct too. This is a write, followed by a read. Exactly. So now we have a write read. Absolutely. You are correct, right? Indeed. Any other suggestion on Zoom?
I think so there's a RB beta and WC beta.
Yeah, here to here. Absolutely. Yeah. So you see, you found a lot of them, right? So the one thing to remember is always alpha alpha or beta beta, but never alpha to beta or beta to alpha, right? So this is, you found many of them. So now I can display. So you see, this is pretty much everything that you can find. Last year, I even forgot one or two that the students found, but now I think that I added all of those that were missing. So these are all the conflicts that we can find in there, right? So, okay, so we'll come back to that one later to make more statements, but basically here we built the graph. Okay, now let's come back to this. Why are we building that graph? Here's the thing. Imagine that now I change the order in which I do things. For example, they read in different orders. What did I do? I just swapped the first two things that they do, right? So instead of R Alice, R Bob, I now have R Bob, R Alice, right? Is it the same? Who thinks it's the same? Yeah, many things think it's the same. Indeed, it is the same. It is absolutely the same. It doesn't matter in which order that is. So what I did is that I swapped a read and a read on the same variable. Why can I do that? Well, I never spoke of a read-read conflict. When you read, it doesn't matter in which order that is, right? So you can swap read-read. That's totally okay to swap read-read. So this is why here it doesn't matter. And this is called the conflict equivalent schedule, the second one, in the sense that it's equivalent. It's exactly the same, and you could swap the order. Now, the way you notice that there is a problem is when there is a cycle in the graph between the people. And for example, let me take this other example here that actually is something that is good, that we like to have. In this case, we have the rows that go top to bottom, but does anybody see that here there is no cycle because all of the rows go from Alice to Bob here? They all go from the left to the right, right? Each row that you see goes from the left to the right. There is no row going from the right to the left. So now imagine that I take this graph here and I squeeze it like that. I squeeze it. So I merge these three and I merge these three. So I get one node here, one node there, and then I keep the rows that went from one to the other. But since all the rows come from Alice to Bob, if I do this squeeze, squeeze, then this is what I get, right? I just have Alice and I have Bob, and it goes left to right. Who agrees, right? This is called, I mean, mathematicians would say that you're using an equivalence relation and taking the quotients by an equivalence relation and so on. But we don't need these fancy words, right? Just imagine that we merge all Alice, we merge all of Bob, and we just look at the rows. So all the rows go from left to right. So this, and since no row ever goes from right to left, then we don't have anything in the other direction. So what's happening here is that I have no cycles. It's always Alice before Bob. There is never a conflict with first Bob and then Alice. What does that mean? It means that now I can start reorganizing up and down like this. You see that I can actually move around my little boxes up and down without ever flipping an arrow, right? The arrows keep going top to bottom, right? Top down. And I can just slightly reorder in that way, in a way that's fully equivalent, because all of my conflicts are respected. So who agrees that this is exactly the same here? Right? This is exactly the same. And now this is actually great because what happens here, look, everything here is Alice, and then everything is Bob. This is great because now it feels like Alice is the only one using the database here, and then Bob is the only one using the database there. This is great. This is exactly the sort of things we want. This provides isolation. But the fact that we know that these two are equivalent means that we call this schedule here, that's called the schedule, we call it serializable, conflict serializable. The idea of conflict serializable is that it is equivalent to a serial schedule, right? So I repeat the definitions. A serial schedule means just Alice and then just Bob. This is serial, right? We can order the people using the database one after the other. It's as if they were just taking turns to use the database. Serializable means that you can reorder a little bit and swap around the transactions. You always have to respect, of course, within a user, it has to be the same order, but across users, you can just move them up and down, right? So here, it was not serial, right? Because you have Alice, then Bob, then Alice. So this is not serial, but it's serializable because actually what you do is you swap these two. This is read-read, so you can swap them in a way that you don't impact any of the conflicts. So this is called serializable. And so what is absolutely fundamental in a relational database management system is that they are able to notice when what the users are doing is actually serializable. So they will let it happen that way because they know that in theory, it is as if it had happened that way, which is something that we like, right? If at some point, however, we are in a situation like this, do you see what happens? We have arrows from the left to the right here. This is an arrow from the left to the right, and we have also an arrow from the right to the left. This is why here, if we try to squeeze all the nodes to all those of Alice and all those of Bob, we have a cycle. We have Alice, then Bob, then Alice, then Bob, then Alice, then Bob. When you have a cycle like that, it is just impossible to rearrange things in a way that would look like that. It just doesn't work, right? You absolutely need to have no cycle at all for this to work. So that gives us actually a pretty good algorithm to figure out whether a schedule is or is not serializable. We just build that graph here that we have here. Then we squeeze the nodes of Alice and of Bob like this, and then we get a graph. If that graph on the users has a cycle, then the schedule is not serializable. We don't like that. And if there is no cycle, then it means that it is serializable and that you can rearrange things in a way that is serial, right? So we like this, we don't like this. What's going to happen in practice is that this PostgreSQL is going to not let it happen. At some point, it's just going to complain or throw an error. No, sorry, you can't do that. That would lead to a non-serializable schedule, leads to problems, okay? Who understands what's going on, right? Okay, so now if we come back to this, can we maybe build the graph? So imagine that we squeeze A, we squeeze B, and we squeeze C. Where are my rows? Well, I see from A to C, and I see from C to A, and I see from A to B, and I see from C to B, and I see from B to C, and from C to B as well. So basically, there's the rows everywhere. So actually, if you tried, you would get that basically, right? Because you will find an row from anybody to anybody. Who agrees with that? Okay, you can look again. You will find, for any two users, you will find an row from A to B, from B to C, from C to A, from A to C, from C to B, and from B to A. You will find for every one of these. So you get basically the complete graph, so to say. This means cycles. This means not serializable. No matter how hard you try, you will not be able to arrange things by pushing them up and down in such a way that there is an order between the users, like first Alice, then Charlie, then Bob. That doesn't work, right? It's basically a spaghetti and yeah, you're blocked. So now what you need to be able to do is, if I give you a schedule like what you see above with these R's and W's and the users as subscripts and the variable written, you have to be able to present them in a table, to put the arrow, to squeeze on each of the users and get a graph like that, and then see if there's a cycle or if there's no cycle, right? You'll have exercises on that, but this is a skill that you'll have, and this is one example of the sort of things that happens in PostgreSQL. So now what happens in reality, concretely for the users, is that when the user starts doing their transactions, there exists in SQL a way to connect to the database and say, begin transaction, you begin the transaction, then you go ahead with your queries, and then you commit the transaction, meaning you say, I'm done with my transaction. So Alice would start the transaction, read alpha, read beta, read alpha, and end the transaction, right? Same here, Bob will start the transaction, write to alpha, read from beta, and write to beta and commit the transaction, right? And what happens is that if people do that and there are no cycles, it's serializable, then PostgreSQL will just let it happen. That's all good. And if at any point something leads to a cycle, when you try to commit, it's going to say, no, 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 you cannot commit because there would be a cycle. So it's basically stopping everything. And then what happens is called a rollback, meaning that everything that the failed transaction was doing is completely ignored and rolled back as if it never happened, right? So if in a transaction, you start a transaction, you write something, and then you attempt to commit, and it fails, that write that you try to do is undone. You cancel it, you remove it, and you roll all the way back as if nothing happened. This is called atomicity, in the sense that when you have a transaction, either all of the transaction happens, all of it, or none of it. You cannot have half of the transaction that is committed and half of it that is not. It's all or nothing. This is called atomicity. For whom is that clear? Right. And you can imagine if you're a bank, that's the sort of things that actually are quite convenient, because what you're going to do is you're going to issue the transaction to withdraw from the bank account and then prepare the banknotes and so on. And either you go all the way to giving away the banknotes and debiting, or you do not give the banknotes and you do not debit. Now, of course, when you are in real life, as you can imagine, once the banknotes are out, the banknotes are out, right? So you also need to take these things into account, right? Okay. And here, to end this lecture, something that terminology that many people will understand in databases is called ACID. ACID properties are properties that many relational database management systems have. It's atomicity, consistency, isolation, durability with respect to transactions, right? Atomicity is what I just explained to you. You start a transaction, then you go ahead, you commit it. Two things can happen. Either the commit succeeds and everything is done, or the commit fails and everything is rolled back as if nothing happens. It's all or nothing. Consistency means that outside of transactions, the database must be consistent. All of these constraints that I told you about, right? It has to be unique, unique values in a column. You can have these check constraints that you have in there. All of that must be at all times between transactions, it must hold. In the middle of a transaction, maybe these constraints could temporarily not hold in the middle of a transaction, but at the end of the transaction, the consistency constraints must hold again, right? So this is a guarantee of consistency. And again, you get that for free from PostgreSQL, right? Isolation is as if you were the only one using the database. This is about these serial schedules. It's first just Alice, then just Bob, and so on. So it's a look and feel. It feels like you're the only user of the database, even though there's a million other people, right? Imagine you're connecting to the online shop. You don't care that there's a million other people browsing it as well, right? To you, it has to look like you're the only one actually on the shop. And durability, D, just means that you're not losing changes, right? So if you wire money to your bank account, you don't want it to be lost, this change, right? So this is if you have a power outage, this has to also be backing up the database and so on. So atomicity, consistency, isolation, durability, ACID, right? So of course, ACID is in order to be easy to remember. And this is something super important because in all of these products, be it PostgreSQL, MySQL, Oracle, IBM, Microsoft, they all provide that sort of guarantees. If you don't use a database system and instead you try to use Python or whatever language and so on, you don't have all of that, right? You need to take care of it yourself. And that's actually very, very challenging. Okay. I think it's almost 11, right? Just a few minutes to 11. So I think you probably deserve a break, and then at 15 past 11, I start with indices. So you got 3 minutes of your time back in order to relax, well deserved. All right, so I'll see you at 15 past 11 for the continuation of the lecture. Thank you very much.